Hello, and welcome to this video on the reflection of waves. When we hear the word reflection, we normally think about the thing staring back at us when we look in the mirror, but all types of waves can be reflected when they strike a surface, not just light waves. All waves can be reflected when they arrive at a boundary between one substance and another. Have a look at this light ray as it's reflected by a mirror. We can draw a normal at the point at which it strikes the mirror. A normal is an imaginary line which is drawn at right angles or perpendicular to a surface. The angle between the normal and the incident ray, that's just the ray that's travelling towards the surface, is called the angle of incidence, I, and the angle between the normal and the reflected ray is called the angle of reflection, R. No matter what type of wave we're dealing with, and whatever the surface, the angle of incidence is always equal to the angle of reflection. This statement is called the law of reflection. Take a look through this example. As you can see, we're looking for the angle of reflection of the light ray from mirror B, so let's give it a go. We'll draw in our reflected ray here, which looks something like this. Then from the law of reflection, we know that the angle of reflection here is going to be 60 degrees. Because the normal is at right angles to the mirror, that means that this angle is going to be 30 degrees, like so. Because the interior angles of a triangle must add up to 180 degrees, that means that this angle is 15 degrees. So if we draw in the normal for the ray which is incident onto mirror B, like so, its angle of incidence must be 90 minus 15, which gives 75 degrees. Drawing in the second reflected ray like this, we can see that its angle of reflection is 75 degrees. So we can write that into our answer space. Wavefront diagrams can be used to describe the reflection of any type of wave from a surface, but it's probably easiest to think about how they can be used to represent water waves. Let's say we're looking at a ripple tank from the top down, and we direct a water wave towards this barrier at an angle to the normal like this. Remember that these wavefronts represent the equivalent points on adjacent waves, so here we could be looking at three wave peaks as they travel towards the barrier. When each wavefront hits the barrier, it's reflected, with its angle of reflection equal to its angle of incidence as shown. The reflected wavefronts then travel away from the barrier in this direction, forming the reflected wave. Make sure you can draw a diagram like this one for your exam. You should start by drawing in the black lines, which represent the path taken by the wave, with the angle of reflection equal to the angle of incidence. Then, draw in the wavefronts, which are always perpendicular to the direction in which the wave is travelling at any point. One of the trickiest things in the entire waves topic is explaining how the image of an object is formed in a plane mirror. To answer that question fully, you'll have to learn how to draw a slightly awkward ray diagram, and we'll get onto that in just a minute. But for now, let's go through the basics. Whoa, nearly forgot my rubber duck. Here we go. A plane mirror is just a mirror with a flat surface. Plane is just a fancy word for flat here. When we look at the reflection of an object in a plane mirror, we're looking at what we call its virtual image. So here, if the real object is on the left, its virtual image is on the right, appearing to be located behind the mirror. This image is always upright. In other words, it's not flipped vertically, and it appears to be the same distance behind the mirror as the object is in front of it. So here, if Ducky is 5 centimeters from the mirror, his virtual image will appear to be 5 centimeters behind the mirror. On to the tricky part now. You could be asked for 4 or 5 marks to use a ray diagram to determine the location of the image of this object in the mirror. Trust me, this isn't one you can bluff, so if you really want those marks, you should learn the following steps off by heart and practice yourself a few times with a pencil, ruler, and piece of paper. First, use your ruler to mark the position of the image, which should be directly opposite the object as shown. Remember here that the distance from the object to the mirror should be the same as the distance from the image to the mirror. Next, draw 2 rays from the object to the mirror like this. Their exact angles don't really matter, but something roughly like this should do you well. You then draw the reflected rays so that they line up with the image. What that means is that if we extended either reflected ray, they would go through the image. Another way to check that each reflected ray has been drawn correctly is to draw in a normal at the point at which the ray struck the mirror. Remember that the angle of incidence should be equal to the angle of reflection. Finally, use your ruler to draw the dotted virtual rays between the mirror and the image. Now that we've finished our diagram, we can explain fully what's meant by a virtual image. If we look towards the reflected rays from this position, it'll seem to us as though they came from the virtual image, even though we know in actual fact that they were reflected from the mirror. A virtual image is an image which is formed by light rays which appear to diverge from a point. By diverge here, we just mean spread out from. A definition which a lot of textbooks give is that a virtual image is an image which can't be projected onto a screen. Here, if we didn't see the object and didn't know that the mirror was there, we might think that there was actually a real object at the location of the virtual image, so if you prefer this version, you could use it instead. If we go back to old Ducky one last time, we can see that all the light rays which appear to have diverged from his virtual image are actually rays from his real version which were reflected from the mirror. Almost there now. As we saw earlier, all types of waves can be reflected when they reach the boundary between one material and another. Sound waves, for example, might be reflected strongly by this brick wall, which is why we might hear an echo if we clap our hands in front of it, and they might be absorbed by a foam wall. That brings us to the end of this video on the reflection of waves. Once you've finished reflecting on the fun we've had over the last 5 minutes or so, why don't you try some of the exam style questions? Practice makes perfect.